Konstantinos Kartas. We'll talk about decidability via the tilting correspondence. Thank you.
Okay, thank you, Christian. Okay, is the sound okay? Can you see the screen?
Yes.
Great.
Good.
So if I'm writing something, can you see?
Yes, it's working.
All right. So I would like to motivate my talk by recalling this very powerful idea in mathematics, which is called the function field analogy. So this is the idea that the rational numbers and in general number fields are in many respects similar to function fields of curves over finite fields. So let me take here the projective line just for simplicity. And there's a huge list of similarities, and there's a dictionary that translates terms from the arithmetic side to the function field side. And via this dictionary, for example, primes correspond to reducible polynomials, and the prime at infinity, in the arithmetic case, corresponds to the absolute value, and in the positive characteristic case, in the function field case, it corresponds to the degree of the polynomial. And all these places are not independent. They are tied together by the so-called product formula, which in the arithmetic case takes the form of the fundamental theorem of arithmetic. And in the function field world, it says that the degree of a principal divisor is 0. So the number of zeros is equal to the number of poles. Now, there is also a local function field analogy, which is the analogy you get by forgetting all of the primes except one. So let's localize the situation by passing to completions. So here we have the periodic numbers. And on the other side, we have Laurent series over a finite field. And at this local level, the similarities between the two fields are even visible from the way the fields are presented to us. So on the function field side, you simply have Laurent series expansions of the form sigma alpha I t to the I over the variable t. And on the arithmetic side, you have something similar by viewing p as a variable, but now you no longer have an embedding of the residue field inside your valued field. You only have a set of multiplicative representatives. And there is also a related fact that addition is not done coordinate-wise. It involves carrying. But nevertheless, the presentations are evidently similar. Now, despite the analogies between characteristic 0 and positive characteristic, there are still many things that are known in one domain and not the other. So let me mention just two examples which are of model theoretic interest. So you have a negative solution to Hilbert's tenth problem over FP round bracket C on the function field side. But on the other hand, the corresponding problem, Hilbert's tenth problem over Q, is not known to be unsolvable, although the problem over the integers is known to be unsolvable. The second example is the following. So you know that the periodics are a decidable field, and you have a very good elimination theory. You know exactly what the definable sets look like. But on the characteristic P side, you don't know whether the Laurent series over FP is a decidable field or not. And as far as I know, at least, there is not even a conjectural description of the definable sets. In order to bridge the gap between characteristic 0 and positive characteristic, which is still evident by the examples that I gave at least. So in order to bridge this gap, people discovered two very beautiful ways of doing this. So the first method is the method of letting the prime p go to infinity. So this was work by Axkochen and Dersov in the 60s, which, among other things, showed that if you take a non-principal ultra product of the p-adics, and you take a non-principal ultra product of FPT over the same ultra filter, then the remarkable thing is that the two fields satisfy exactly the same sentences. So Axkochen actually used this asymptotic equivalence between the p-adics and FPT to resolve a conjecture by Artin, at least in its asymptotic form, which was about the existence of non-trivial solutions, non-trivial zeros to homogeneous polynomials, which have a large number of variables. So they managed to transpose a result on the characteristic P side by Lang and transfer it actually to characteristic 0 for large prime P compared to the degree of the polynomial. The second method, okay, there are other applications which I will not discuss now, because I actually want to focus on the second method, which is perhaps less well known to model theorists. And it's the method of letting the ramification go to infinity. So it's a totally different game. So now you fix your prime once and for all. But instead of looking at QP, you look at something like QP with nth power roots of P, and you think of n as being large. And again, you have a similarity between QP with an nth power root of P, an nth root of P, and FPT. Okay. So this is the Krasner-Kasdan-Delin principle, which essentially tells you that the larger n is, the greater the similarities between those two fields are. So this is made precise by Delin's theorem, for example, which gives you an almost isomorphism between the Galois groups, except that you need to mod out by an error coming from the ramification, from the filtration of the Galois groups. And in the limit, you actually get an outright isomorphism between the corresponding Galois groups, say of these fields here. So if you take QP with P power roots of P, and you take the perfect hull of FPT or FPT itself, it doesn't matter, then the Galois groups, the absolute Galois groups of those two fields are exactly the same. And this was a theorem by Fontaine and Winterberger, which actually preceded Delin's theorem. So Delin's theorem came after. So in recent work by Peter Scholze, these ideas were vastly generalized in the general context of perfectoid fields and also in higher dimensions, where he also introduces the tilting functor, which is a formal way of really getting from characteristic 0 to positive characteristic. We will see this in how this is defined in a few slides, and we are actually going to use it. But the main takeaway actually from this slide is, well, so all this essentially suggests a program for us. And this program consists in two parts. So the first part is to actually use these ideas contained in this red box to prove new results in the model theory of Henselian fields. The second part of the program is in the reverse direction. It's about understanding the underlying model theory of this arithmetic phenomenon, and then really using model theoretic tools to prove new results in arithmetic. So for the most part of this talk, I will be talking about the first part of the program, going from these number theoretic observations to the model theory of Henselian fields. But there are some things to say also about the second part of the program. So near the end, I will be discussing, if I have time, a model theoretic way to see the Fontaine-Winterberger theorem. Okay. So yeah, this is the outline of the talk. First, I want to discuss a few questions which are of interest. So I think I mentioned before that we have a good model theoretic understanding of the p-adics. There are also quite a lot of results about finitely ramified extensions of the p-adics, but there are virtually no results about infinitely ramified extensions, such as the ones that are listed here. So here you have, okay, some of these fields we saw before, QP with p power roots of p, QP with p power roots of unity, and QP abelian. And we would like to know if these fields are perhaps existentially decidable, or more ambitiously, if they are decidable. And we would also like to know the definable subsets and so on, but this is already going too far maybe. Okay, so the second example was mentioned by McIntyre in his survey 30 years ago. And the third one was mentioned more recently by Johann Koenigsmann in ICM, where he also gave a conjectural axiomatization of the theory. Okay, it's not known to be complete. Yeah. But in the spirit of the previous slide, we also want to relate these questions or these mixed characteristic objects with their positive characteristic analogs. So here we have the perfect hull of FPT and also the perfect hull of FP bar of T. And you can again ask the same questions, whether the existential theories are decidable or not, and also whether the full theories are decidable.
Can you remind us what these languages are?
So, by the way, was not
Can
able
you
to
remind
question.
what the languages are?
Oh, so here, so the language of
Elval.
valued fields, I guess, is known. But here, I mean the language of valued fields with a parameter for T.
And Elval is just with the divisibility relation.
I mean, it doesn't matter which formalism you choose. Let's say, just to fix things, I mean, you can just work with a unary predicate for the valuation ring. You can work in a three-sorted structure where you have the associated residue maps and valuation maps, or you can work with the divisibility relation.
Right.
Doesn't really matter.
Thanks.
Okay, but what's important, and so let me emphasize this, is that on the characteristic P side, you include a constant for the element T. This will be really crucial. So it's good actually that this was mentioned now. Okay, we will see how this comes up later. So what we're going to show is that A and B from the mixed characteristic category are related to A. So in fact, we will show that, for example, this field is decidable or existentially decidable relative to the perfect hull of FPT. Same for B. And similarly, QP abelian is going to be existentially decidable or decidable relative to the perfect hull of FP bar of T. But it's really important that we include the parameter T here. Okay. So yeah, before I continue, let me say that these results actually fit into the larger framework of perfectoid fields. So now we're going to show a relative decidability theorem for perfectoid fields, which will roughly say that whenever you have a perfectoid field, it's decidable relative to its tilt. Okay, this will not quite be true. You need to add a natural ingredient, but that's where we're heading essentially. So at this point, most people are familiar with the basics of perfectoid fields, but let me nevertheless remind you a few things. So in case you're not familiar with this business, Let me say that it's much better to stick with examples actually. So just take the examples that we had before, but you also need to complete them. Okay, they are not complete. And in general, a perfectoid field is a non-Archimedean valued field, which is complete. The value group is embedded in the reals, but it's non-discrete. So things like QP are already excluded. And the rest during is semi-perfect. So the Frobenius map modulo P is surjective. Okay. Now, whenever you have a perfectoid field, you can tilt it and get a perfectoid field of characteristic P. This is called the tilting construction or tilting functor, and it's only really interesting when you started from something in characteristic 0. Otherwise, it will not do anything meaningful. Well, you will just get the same field back, essentially. So how does this work? First, you define the underlying multiplicative monoid of the tilt as follows. So you consider K infinitely many times, and consider the inverse system where the maps are, well, each map is x maps to x to the p. Okay, it's not a ring homomorphism or anything, it's just the map, it's multiplicative. You can consider the inverse limit, it gives you something. So this something you can think of as the set of compatible systems of p power roots of elements of K. So you have things like that. And you can multiply coordinate-wise, but if you want to define addition, it will be more complicated. It's not, addition is not defined coordinate-wise, simply because taking p roots in characteristic 0, for example, is not going to be additive. So in fact, you need to tweak the definition in the case of addition. You need to take some sort of limit. And this is, well, this is the first point that you see that complete, well, the assumption that K is complete is actually necessary for this construction, and Cilianity is not enough. So what is this? So if you just want to compute, let's say, the 0th coordinate of the sum, it's simply going to be something like this. And then you take the limit. Okay, so this is the 0th, just the 0th coordinate, just to give you an example. And you can check that this is a Cauchy sequence in the topology of K. And the limit is precisely the 0th coordinate of the sum of the sequences xn and yn. And for the other coordinates, you need to do some shifting. So now, the tilt is essentially this set, that's the underlying set, with a coordinate-wise multiplication and this addition. And there are many things to check. You first of all, well, you need to check that it's a field and so on, but everything works out. And then you can also define a valuation on K flat by saying that, well, just take the first element, take the valuation with respect to K, and that's the valuation of the sequence. Okay. So here are the examples that we mentioned before. So it turns out that if you tilt QP with p power roots of P, and if you tilt QP with p power roots of unity, you actually get the same thing. You get the completed perfect hull of FPT in both cases. This example already suggests that untilting, whatever it is an ambiguous operation. Starting from a tilted perfectoid field, you cannot untilt it uniquely. There is some ambiguity involved. So now I want to talk about this. So what I said is that if you start from a characteristic P perfectoid field, so something like this, in general, there will be many things that tilt to it, many characteristic 0 perfectoid fields that tilt to F. In fact, there will be a curve which parameterizes all the untilts, and in general it will have infinitely many elements, and it's precisely a result towards the construction of this curve that we are going to use for our main result. So let's see how this works. So now I want to describe the untilts of f in an intrinsic fashion. So this means in a way that depends only on the arithmetic of f itself. So the way you do this is you first build the ring of Witt vectors over OF. Then the untilts of f are essentially encoded in the so-called distinguished elements of the Witt vectors. So what is a distinguished element? A distinguished element is a Witt vector here, whose Witt vector expansion has the following properties. The first coordinate, the 0th coordinate, is in the maximal ideal of f, of OF, and the second one is a unit in the valuation ring. So if you wanna, sometimes this is called primitive degree 1 element, simply because you can write it in this form. And if you write it in this form, so here U is a unit in the Witt vector. So if you write it in this form, well, it sort of looks like a degree 1 polynomial in the variable p, so to speak. So that's why it's sometimes called primitive degree 1 element. Now, okay, so now this is the correspondence that you get. So distinguished elements correspond to untilts. Well, not quite. You need to take the ideals generated by distinguished elements in the Witt vectors. So distinguished elements modulo units in the Witt vectors. So let me describe briefly how this correspondence works. Actually, we will only need this forward direction. So let me just describe this. It is very straightforward. Well, it's very straightforward to describe, but there are still something that one needs to check. So if you give me a distinguished element or the ideal generated by a distinguished element, well, the way I produce for you an untilt of f is by taking the quotient of the Witt vectors by this ideal. And as it turns out, this is the valuation ring. Well, this is a valuation ring, first of all, and it's also a valuation ring of perfectoid field of characteristic 0. And it's also the valuation ring of a perfectoid field of characteristic 0, which actually tilts to f. So that's how you get the untilt from the distinguished element. Now, okay, let me not describe this. Now, but let me say a few words about this. So just by looking at this equation right here, or isomorphism, Rideau and Scanlon actually showed that there is a bi-interpretation of K between K and its tilt in the sense of continuous logic. Okay, this is how to, well, this is one direction. The other direction is essentially by the definition. So this provides you an interpretation, for example, of OK inside the tilt, but it's really an interpretation in the sense of continuous logic, because essentially what goes wrong if you try to transpose this into ordinary first order logic is that if you give me a sentence about OK and I use this isomorphism, well, essentially it converts to a sentence somehow about the tilt, but well, I need to introduce infinitely many variables for the coordinates of the Witt vectors. So it's not going to be a sentence in the sense of ordinary first order, well, in the sense of first order logic. So in order to transpose things in first order logic, we need to do some additional work. And there is also, well, okay. This actually motivates, if you try to transpose things in the ordinary first order logic, then you will inevitably discover this notion of a computable untitled. So what is this? So just to motivate the discussion, let me repeat again what I said before, that if you start from something in characteristic P, maybe it's this one, you will have too many untilts in characteristic 0. And in fact, not only you will have too many untilts up to isomorphism, you will have too many untilts up to elementary equivalence. And this already tells you that you cannot expect a naive statement like if the tilt is decidable, then so is K. This will simply not work just for cardinality reasons. So one actually needs to restrict him or herself to computable untilts. So here's the setting. So now I will define this. The setting is, well, you start with F, it's characteristic P perfectoid field. And let's also fix a computable subring of OF. So this means that it's identified with the natural numbers in such a way that the ring operations are recursive functions. So this is the usual example that we have. And you can take R0 to be just a polynomial ring. Okay, that's the Farks-Fontaine correspondence from before. And here's the definition of a computable untilt. So first of all, it's an untilt. And here comes the important condition. So take the Farks-Fontaine correspondence. So write your valuation ring in this form. But now impose the condition that there is a generator Xi, which is actually a computable which has a computable bit vector expansion. So in other words, you really have an algorithm to produce the nth digit, the nth bit vector digit. So first of all the coordinates lie in this computable subring that you started with. And second, this function that returns the nth digit is recursive. Okay, so this is just the usual way to define those things. So it's very similar to the notion of a computable real number or a computable p-adic integer. Okay, so in the case of p-adic integer, you simply have an algorithm to produce for you the nth p-adic digit. That's the definition. Okay, so this is going to be important. So now we're almost ready to state the main theorem. But first, let me discuss this result by Van den Dries in the 80s, which is an unpublished result, and says the following. So this is an Axe-Coates-Nersov principle, but as you can see, there are no restrictions on the ramification whatsoever. It's a very general result. And what it says is that the theory of K in the language of valued fields simply depends on the theories of all the residue rings for all natural numbers n, and the theory of the pointed value group. So what this means is that if you give me another mixed characteristic Henselian field, K prime V prime, and the corresponding residue rings are elementary equivalent for all n, and similarly with value groups, then you get an elementary equivalence between the value fields. Okay. So let me say a few words about the implications of this theorem with regards to decidability. First, let me say what this theorem does not imply. This theorem, it tells you actually that the theory of K is axiomatized just by putting together the theories of all the residue rings, so to speak, and the theory of the value. What it doesn't imply is that it's decidable relative to all of these residue rings and also the value group. So in fact, you can cook up examples of mixed characteristic Henselian fields where each individual residue ring is decidable in the language of rings, and the value group is also decidable, but K itself is not decidable in the language of value fields. So this is, what's the problem here actually? Why doesn't it imply that? Well, the reason is that you can have a bunch of nice theories of residue rings and also the value group. Okay, and these are individually, these are all nice theories. You have a recursive axiomatization and so on. But somehow we are familiar with the fact that if you take a union of recursive sets, it's not necessarily recursive. So somehow it can be the case, it can happen that when you put all of those nice theories together, you create chaos. However, this theorem does imply something, and that something is a little bit more subtle. So you actually need to assume that the sequence of residue rings is uniformly decidable. So this means that you have an algorithm so that whenever you're given an input n, phi, where phi is a sentence in the language of rings, let me say it this way. So you have this function which takes a pair n, phi, where phi is a sentence in the language of rings, and returns 0 or 1, depending on whether O mod p to the n models phi or not. And you're asking that this function is recursive. So this, of course, implies that its individual residue ring is decidable, but it's much stronger. Okay, so here's the theorem. So now you assume that K is an R0 computable untitled of K flat for some R0. And now you can really lift decidability from characteristic P to characteristic 0. So if the tilt is decidable in the language with parameters from coming from the computable subring, then you get decidability of K in the language of value fields. Okay, and let me stress again that if you omit the parameters here, this statement is false. So how do you do this? So here's the statement again, okay? So the first key idea is to use the Farx-Fontaine correspondence that we saw before, but now you truncate the equation, the isomorphism modulo p to the n in some sense. So just take the isomorphism that Farx-Fontaine gives you and mod out by p to the n, which will actually give you an honest interpretation of O mod p to the n inside the tilt, with parameters for the n first coordinates of the Witt vector. But as we saw before, okay, so this already tells you that each individual residue ring is decidable, but sorry, is there a question?
No, just a sneeze.
Okay, yeah. So now you're almost in a position to use Van den Dries. There is this subtle point that we discussed before, of uniformity. But here comes the assumption that we haven't used so far, which is that K is an R0 computable untilt of its tilt. So by using this, you actually get, not only do you get an interpretation of its individual residue ring inside the tilt, you actually get a sequence of interpretations which is uniformly recursive. And this actually gives you the uniform decidability of the family, of the sequence. So what does it mean for a sequence of interpretations to be uniformly recursive? Well, it's sort of the same as before. So the function that takes n comma phi to the reduction of the nth interpretation map, phi gamma n, is a recursive function. Okay, so this is really a subtle point, but it's really important. And let me emphasize that it's not about the uniform interpretability of O mod p to the n in the tilt. It's totally different. It's about the uniform recursiveness of the sequence of interpretations. Okay. So why is this useful? So, well, here's a corollary, which is about the fields that we saw before. So if you assume that the perfect hull of FPT is decidable or existentially decidable in the language with a parameter for t, then you get decidability or existentially decidability for these two fields here. But it will not be the case that every untilt of FPT, well, first of all, yeah, I'm talking about untilts, but of course you notice that these fields are not complete here, but this is really a minor issue when it comes to decidability. Okay, so it will not be the case that every untilt of the completed perfect hull is decidable. You can simply construct too many of them, which are pairwise elementary inequivalent. But these two specific fields will be decidable or existentially decidable depending on what you assume. Okay, and you have a similar story for QP abelian. Okay, here, let me erase this red line because here I mean the perfect, the algebraic closure of P. So the additional work that you need to do is to actually compute the Witt vectors now and convince yourself that these are, well, these have computable computable Witt vector expansions. So the first one is really trivial. Well, it's not trivial to compute the Witt vector, but once you know it has this simple form, then you know that this is a computable untilt, essentially, of the perfect hull. And for the other two, it's a bit more complicated, but again, it has a relatively simple form. So I have not written the p-adic expansion of this Witt vector, but if you want, you can use the addition law for Witt vectors and so on, and you can compute actually the p-adic expansions. So yeah, so these are computable Witt vectors, and you can essentially conclude by the previous theorem, modulo this thing with a completions and so on, which is not really an issue. But this is just a conditional result. So can we actually use this theorem to say anything absolute? So you can. So you can say that, okay, maybe you don't know if QP with p powers of p is decidable or not, but you can show that it admits a decidable maximal immediate extension. And again, I emphasize the word a. So this will admit many maximal immediate extensions, and in fact, most of them will be undecidable. But there is a special one. Well, I'm not sure how special it is, but there is one which is decidable. And the proof essentially goes by transposing a recent result by Lisinski, which generalizes earlier work of Kuhlmann on tame fields of characteristic P. So essentially what you do is you take the field that you're interested in, you take the field. Here you take a special maximal immediate extension. So this is the Hahn field, where gamma is the P divisible Hal of the integers. And you untilt it essentially. So I said before that untilting is ambiguous, but in fact, if you fix a perfectoid field in characteristic 0 and it's tilted, then actually untilting becomes unambiguous. You actually get an equivalence of categories. An equivalence between the categories of perfectoid field extensions, let's say. It's much more general than that, but yeah. So when you untilt something, which is above the perfect Hal of FPT, then the associated bit vector remains the same. So it's still going to be this guy. So you get that this is going to be a decidable field in the end. And also it's going to be an immediate extension because tilting preserves inertia degrees and ramification degrees. And it's also going to be maximal because tilting preserves maximality. So yeah, this is, okay, so this is, as far as I know, the first decidability result for tame fields in mixed characteristic. You can also prove something similar for QP with P powers of unity, and also for QP abelian, but in the case of QP abelian, it's known. And in that case, there is a unique maximal immediate extension. Okay, so this is something you can do. The other thing is you can show unconditionally that your valuation ring modulo P is existentially decidable. So this you can show by transposing results by Anscombe-Fehm in the language of valued fields. Okay, I'm not going to present the proof. It's essentially just a small trick. Okay, but you can somehow transpose this resulting characteristic P to get this. But for higher residue rings, actually, it seems very unlikely that you will be able to eliminate T from the language in characteristic P. You will probably need stronger results in the language with T. Okay. How much time do I have, by the way? I'm not sure.
You have like 10 minutes, 10, 15 minutes.
Ah, okay. Yeah, so now I'm going to move to something a little bit different. So I'm going to talk about the theory of so this is another this different stuff, but it uses very closely related ideas. So it's about the theory of all p-adic fields with a fixed prime P. So in other words, I want to understand the theory of finite extensions of QP, of all finite extensions of QP for a fixed prime P. So as far as I understand, this is an old problem. I mean, it appears in the work of Derexon and McIntyre, but many people have told me that it's much older than that. Maybe it was Sterling. I'm not entirely sure. Anyway, we want to understand this. So whenever you have a collection of structures and you want to understand the theory of all of them, the first step towards understanding it is to study the asymptotic theory. So the set of sentences which are true in all but finitely many structures of your collection. Or equivalently, you want to study the theory of all non-principal ultra products from structures, taken from structures in your collection. These are equivalent. Okay, so the classical example is the theory of finite fields, where you first study the pseudo-finite fields, essentially. Okay, so now, towards understanding the asymptotic theory of this collection, we actually encounter an undecidability result, at least in the presence of a cross-section in our language. So the asymptotic theory of p-adic fields is undecidable in the language of value fields with a cross-section. So so this is what we are going to prove. And let me say how this compares with the classical results in the literature. So first of all, let me emphasize that its individual K, its individual finite extension of QP is decidable, even in the language of value fields with a cross-section. So this is this classical work by Kozin and Ersov. Okay, I'm not sure if Ersov was working with a cross-section, but anyway. And maybe they did not state it for finite extensions of QP, but well, these are interpretable without parameters in QP itself. Okay, anyway. So this is one thing. The second thing is that if you take the asymptotic theory of all QP, but now you allow P to change, then this is decidable. Again, also with a cross-section in the language. This essentially follows from Ack's result in pseudo-finite fields. It's also in the paper, actually. And in the same paper, he proves something for a fixed prime P. So this is where P changes, but this is going to be for a fixed prime P, where you only consider the unramified extensions. So not all extensions, but only the unramified ones. And again, the asymptotic theory or the full theory, whatever you want, is going to be decidable. On the other hand, in characteristic P, we mostly have undecidability results. So FPT is undecidable with a cross-section. This was actually already known to Axe, but it was unpublished. The first published proof was by Becker, Denef, and Lipschitz. And 10 years later, Fidas actually showed that already the existential theory is undecidable. And in fact, he also showed that you can take this base field to be anything that you like, as long as it's of characteristic P. So what's a bit interesting here is that although this statement is about mixed characteristic objects, we will see that in fact, this theory is much closer to characteristic P than characteristic 0. So although in characteristic 0, in mixed characteristic, you have all these nice decidability results, in fact, when you want to deal with this structure, it turns out to be much closer to positive characteristic for reasons that I mentioned in the very first slide of this talk. So how do you do this in practice? So the idea is to adapt Fidas undecidability proof for FPT with a cross-section. So let's see how you can do this. First, you isolate the difficulty with this collection, which lies precisely in unbounded ramification. So you can simply encode the asymptotic theory of totally ramified p-adic fields. So if you want to check a sentence phi about this asymptotic theory, well, you simply check the sentence K equals FP implies phi in the asymptotic theory of all of them. So this first step is important, but it's easy. So the second step is to note that if you have a totally ramified p-adic extension and you mod out the valuation ring by p, then you get a truncated polynomial ring. Or actually, it's much better to think of it as a truncated power series ring. So this is a standard calculation, which I will not do here, but it's not very difficult. However, it's important. And this is the calculation that allows us to do the reduction to positive characteristics, essentially. So in step 3, so this calculation essentially allows you to encode the asymptotic theory of all those truncated polynomial rings together with a predicate for powers of t. So there is a subtle point here. And the subtle point, well, you want to say something like, okay, essentially the asymptotic theory of all these truncated polynomial rings is essentially the asymptotic theory of the valuation rings modulo p. But in order for this to work, you actually need to ensure that each of those truncated polynomial rings arises finitely many times as a residue ring modulo p. But this is true because for any fixed ramification degree, there are finitely many totally ramified p-adic extensions of degree e. So in fact, you will get only finitely many copies of its individual valuation ring. And this is good enough to say that the theory, the asymptotic theory of, well, all the residue rings modulo p is precisely the asymptotic theory of all of those truncated polynomial rings. So there's a subtlety there which has to do with well, what I mentioned. Okay, you also get a predicate for powers of t, which comes from the fact that if you take your cross section and you project it modulo p, and you use this isomorphism, then, well, maybe your choice of a uniformizer was not correct, and you actually need to argue that for any choice of a uniformizer, you get an isomorphism from O mod p to this truncated polynomial ring. But the point is that the image of the cross section will exactly map to the set of powers of t in the truncated polynomial ring. So that's why you get this. So steps 4 and 5 are really the steps where the main technical, the main technical calculations lie. But essentially, you just adapt Fidas undecidability proof for FPT. So this proof goes by eventually encoding the positive extension theory of the natural numbers in the language with addition and p-divisibility. So here you can do something similar. Now you don't have power series, but you still have truncated polynomial rings, and then goes to infinity, so that's good enough actually. So you first encode the intervals. So this is a notation which means the numbers from 0 to n-1. And you also have an element for infinity. And addition behaves exactly as you expect, except that when the sum is too large, you declare it to be infinity. When the sum is greater than n, greater than or equal to n, you just declare it to be infinity. And p-divisibility is almost what you expect. For technical reasons which I will not discuss, you will need to restrict it in a sub-interval of n, but anyway. Once you have this asymptotic theory, you can actually encode the Diophantine problem for the natural numbers with addition and p-divisibility. And the idea is that if you give me a system of equations involving also p-divisibility, and you ask me whether it has a witness in the natural numbers? Well, I simply check if it has a witness in a large enough fragment, in a large enough interval, so to speak. And if it does have a solution in a large enough interval, well, you're not exactly sure that it's a solution because you may have weird things going on with infinity and so on. But essentially, you can restrict yourself away from the horizon so that no weird things are going, no weird things come up. Everything reduces to the ordinary counterpart, to its ordinary counterpart. So you have no weird things adding to infinity, and well, P divisibility is well behaved. And then actually you can get a witness back in the natural numbers. Okay, so this is essentially the idea. Well, this involves some technical calculations, which are also quite interesting, but I will not bore you with details here. Maybe I'm already actually.
Yeah, I think it's time to wrap it up.
Okay, so yeah, so maybe I'll talk about this another time. Okay, so let me thank some people and oh well, okay. Let me see if there are questions.
Okay, thank you very much. So, are there any questions?
I just will invite you to the GTM to get the sequel.
Is that Zoe speaking? I mean, I cannot hear anything. Well.
No, I was saying that I was joking. I was saying maybe we invite you to the GTM to get the end of the story.
What is the GTM?
It's a seminar whose name is Geometry and Model Theory.
In Paris.
Yeah. Well, yeah. I mean, yeah. I would be happy to continue this, of course. Yeah.
Okay. So, any other questions?
Yeah, I guess I had a question. It's a stupid question, sorry. But you mentioned that the untilts were defined up to modulo units, right?
Yeah. Mm-hmm.
Now, it seems to me that this means that you only need to know psi 0 in a sense.
No, not really.
Not really?
No. Well, psi 0 really contains 0 information. You need to know much more.
But what are the units? Aren't the units things which aren't they determined by their first coordinates?
Well, yeah, let me go to this.
I mean, isn't a thing a unit if and only if it's a unit in the first coordinate?
Yes, I guess this is true, but you need to know much more.
Okay.
I mean,
okay.
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 I'm not sure what you're asking. Let me see. So, I mean, if you have, so say you have an ideal psi, right?
Yes.
So psi is given by psi 0, psi 1, blah, blah, blah. So suppose you only know psi 0, then I don't think you know the ideal generated by psi. I mean, what is it? Is it just, are you saying this?
Yes, I was wondering. Yes, exactly.
No, that's not true, actually, because you might have something.
Okay.
But I can tell you why, actually. I can tell you. So the problem, so I guess what you're thinking is that, okay, just factorize psi 0 and then whatever you have will be a 1 unit, right? That's what you're thinking, probably.
Yeah.
So you're just saying, take this psi.
Okay, it's because OF is not a field. Okay, fine.
Exactly. So when you factor out t squared, okay, you get a 1 here, but what do you get here? You cannot write this, as you said, it's not a field.
Okay, okay, yes, that's the problem. Okay, thank you, sorry.
Yeah, no problem.
If OF was a field, it would be correct, but it's not a field.
Yes, exactly.
Mhm.
Any other question? Maybe in the chat, in the online thing? No. Actually, I had one question. You mentioned that if you know that the decidability of the completion implies the decidability when you apply the untilting thingy.
If you know the decidability of the completion.
Yes, you had the decidability of the field because they are not perfectoid, right?
Yeah, you're talking about the difference between Henselianity and complete and the complete business, right?
Yeah, yes.
So so what do you want to know about this? How do you deal with this essentially, right?
Yeah, yes, exactly.
Okay. So the way you deal with this, so let me give you a quick answer. Well, let me give you two answers actually. So the first answer is that first of all, you don't care about characteristic 0, whether you complete it or not, because this theorem of Van den Dries actually tells you that, well, if you're dealing with this, at least if you're dealing with rank 1 valuations, essentially K is going to be elementary equivalent to K hat. So the reason is that O mod P to the n is canonically isomorphic to OK hat modulo P to the n. And the value groups are going to be isomorphic as well. So you can actually apply Van den Dries to tell you, to deduce that K will be elementary equivalent to its field whenever K is a Henselian field, let's say, of mixed characteristic and the value groups of rank 1. So in characteristic 0, you don't really care whether your field is complete or Henselian. Now, this is also true in characteristic, regardless of the characteristic, I think there is an unpublished result by Scanlon and by Rideau and Scanlon, which I just saw this a few months ago, which is a general quantifier elimination result via which you can do things like you can show things like this.
Kostas, this result is not true.
It's not true, really?
No. We made them. There is a hole in the proof.
Oh, okay. So
yeah, I would very much like it to be true, but it doesn't work.
Yeah. Okay.
No,
so
yeah,
never mind about that. Okay. So in characteristic 0, you can use this. In characteristic P, maybe you can't. Okay. So the first answer is incomplete.
We don't know that it is false, but we don't know that it is true either.
Okay. So let me put a question. So the second answer, which is actually the way it's presented in the paper, is to show that essentially this business goes through when you consider truncated, when you consider essentially the truncated versions of the valuation rings. And you can show that, for example, when you mod out by something like this, it's actually going to be canonically isomorphic to the completion. So essentially, this whole argument goes through just by working with the truncated versions of the polynomial rings. So it doesn't matter whether you consider OF or the completion.
Okay. Any other questions?
Yes. Hello. Oh. Okay. Hello. Yeah, I had a question coming a bit later. Your result about decidability, maybe.
Yeah.
The unconditional result, and you said that you said there is a decidable extension.
Yes.
But I wonder, do you have any? I mean, is that a very special extension, or do you have any idea what proportional are decidable, or are there?
To be honest, I have no
I mean, do you have an idea about the rest? Yeah, about here. Yeah.
I have
Also,
no
yeah.
idea. What I can tell you is that maybe I have some idea actually. So I can tell you that most of the most of the maximal immediate extensions will be undecidable.
Okay.
So the way you do this is you can build a tree essentially of extensions of this guy. And if you look at the roots of the tree or something, you will get, if you look at the roots of the tree, you will have some extensions. Then you take maximal immediate extensions of them, and you will see that most of them are actually undecidable because they are pairwise inequivalent. So just to be concrete, what you do is something like this. So it's a tree-like construction. So let's say here you join a pth root of p, and here you adjoin a pth root of u times p, where u is an element that has the property that taking a pth root of that produces the unique unramified extension of, okay, maybe this is too technical, but anyhow, the point is that you can produce too many pairwise inequivalent maximal immediate extensions for this guy. So in fact, most of them will be undecidable. Now, I don't know if there is another decidable maximal immediate extension. I only know this guy. And the same is true actually for the perfect half of T. As far as I know, the only decidable maximal immediate extension in the language with T is the Hanfield. I don't know of any other example which is, I mean, all of these things are decidable. All of the maximal immediate extensions will be decidable in the language of value fields. But in order to transfer decidability, you need the language with the parameter for T. And this is the only guy that I know who is decidable in the language with T.
And is that this Lisinski?
This is Lisinski.
Okay. Okay, thank you.
Yeah, no problem.
Okay, so if there are no further questions, we can thank again Konstantinos.